Hey guys, I'm going to be going over 4.2 homework. So we're using properties of exponents and we're simplifying each expression right here. So starting with question 1, this right here, what we're going to do, so I have a power to a power. And a power to a power means I can multiply them together. And so this expression is 12 to the when I multiply 2 by 1/4, that's equal to 1/2. So 12 to the 1/2. Right? And that's equal to the square root of 12. Okay, and the square root of 12 is equal to the square root of 4 times by 3, and I can take the square root of 4, which would be 2, and then I'd be left with the square root of 3. Yeah, I think that's right. Let me just check one thing. Yep, that should be good right there. Yeah. Okay. Yeah, that's good. All right, and then for this expression right here, I see that we're dividing, and both expressions have a base of 7. This 7 is to the first power, and if you're dividing two expressions and they have the same base, then we can subtract their exponents. So this would be equal to 7 to the 1 minus 1/3, and 1 minus 1/3 is 2/3. So this can be written as 7 to the 2/3. Okay. For this next one right here, I can go about this in I was gonna say a couple different ways, but maybe not. But no, I guess I can. So because I have a quotient and both these quotients have powers and everything is being raised to the negative 1/3, I could multiply both powers by negative 1/3. I could do that first. Or I could rewrite this to be 9/6 to the third raised to the negative 1/3. So since they have the same power, I can rewrite it as one quotient with one power rather than a quotient with two powers. And now I can multiply this right here. I have a power to a power, so that's going to be equal to, well, I can also simplify 9/6 now, because 9/6 is equal to 3/2. So that would be 3/2, and then 3/2 is going to be raised to the negative 1 power, because when I multiply 3 by negative 1/3, that's a negative 1. And then with negative exponents, I can use the reciprocal, so this would be equal to 2/3 to the first power. But I don't really need to write it as to the first power, so I'm just going to write it as 2/3. Okay, let's see here. So, you can kind of do the same thing as we did in this one, although we had a quotient, or this one right here. We had a quotient and the bases were the same. This time we have a product and the bases are the same. And so since the bases are the same, instead of subtracting them like we did up here, we can add them. So we can change this to be 5 to the 1/2 plus negative 3/2, so that's just going to be minus 3/2. And then all that's going to be raised to the negative 1/4. And then, so when I add these right here, they have the same denominator, so 1 minus 3 is going to be negative 2/2 raised to the negative 1/4. Okay, and that's going to be equal to 5 to the negative 1 to the negative 1/4. And now I can multiply these powers. So that's going to be equal to 5 to the 1/4. Okay. For this one right here, a lot to do with this one right here, but I can start with the numerator. I see that they have the same base, so I can add those. So this would be 49, and then because I'm adding these and they have the same denominator, that's 3 plus 7, so that's going to be 10 over 8 over 7 to the 5/4. Okay, and then I'm going to reduce this right here. 5/8 is, or 10 over 8 is the same thing as 5/4. So this is 49 over 7, and that's raised to the, to the 5/4, 7 to the 5/4. And now that they have the same powers, I can actually write it so it's 49 over 7 to the 5/4. And then I can divide 49 and 7, so that's going to be equal to 7 to the 5/4. Just like that. And I think we can leave it like that. Okay. For the next one, use the properties of radicals to simplify the expression. Okay, so because these are both cube roots, I can multiply what I have inside. So this is the cube root of 16 times by 32. So I'm going to do 16 times by 32, and I get the cube root of 512. Now what I'm going to check here is to see if 512 has any cube roots. And so you can do prime factorization with that. Let's see. So let's take 512. Let's divide 512 by 2. So 512 divided by 2 is 256. Okay, let's take 256. Let's divide that by 2. And I get 128. Divide that by 2, and that's going to be 64. Now see here, well, wait a minute. Why don't I just try 512, the cube root of 512? Why don't I just try that? Aha, there we go. So I don't have to do all that. 512 is a perfect cubed. It's going to be equal to 8. 8 multiplied by itself 3 times over is 512. So there we go. Okay. Here I have fourth roots of 8. So that's going to be equal to fourth root of 64. I don't believe, so 64 raised to the 1 divided by 4. Okay, so it's 64 doesn't have a fourth root, a perfect one anyways, a whole number. So again, think of 68. 68 is equal to the fourth root. So 16 is a factor of 64. And 16 has a fourth root, which is 2. So 64 times by 4. So 64 times by 4 is 64. And the fourth root of 16 is 2. So this is 2 fourth root of 4. Okay. All right, here, so I have square root of 2 divided by 32. That's equal to, they're both square roots. So that's square root of 2 over 32. Which is equal to the square root of 1 over 16. And 16 and 1 have both square roots, so that's equal to 1 over 4. Okay, now here we have cube roots, all of these right here. So since they're all cube roots though, so I can put them all just under one cube root. So 6 times 72 over 2. And what is 6 times by 2, or 6 times by 72? Divide that by 2. So that's equal to the cube root of 216. Does that have a cube root? Yes, it does. It's equal to 6. Okay. Write an expression in simplest form. Alright, so we're going to simplify radicals. So 567 does not have a fourth root. So we're going to try and see if 567 has factors that are fourth roots. So 567. So I'm going to try and divide 567 by perfect fourth roots. So let's see what this fourth roots. So let's see numbers that are perfect fourth roots. Always 1. 2 is not, so you can do this by doing 1 to the fourth. 1 to the fourth is 1, and then 2 to the fourth is 16. 3 to the fourth is 81. 4 to the fourth is 256. Okay, I don't think we need to bother going much further than that. So I'm going to see if any of these numbers right here divide perfectly. I'm going to start with this one, see if this divides into that. So 567 divided by 256, it does not divide into it. So now I'll do 267 divided by 81. So 567 divided by 81. And I get 7. So this right here divides into that. So I have the fourth root of 81 times by 7, and the fourth root of 81 is 3. So 3 fourth root of 7. And there we go. That's its most simplified it can be. Okay, now here I can combine this to, I know what we're going to do here. So in this case right here, we're trying to simplify by making sure that we don't have a radical in the denominator. Okay, so basically what I can do is I can multiply top and bottom by the same number, but I can do it in such a way where I can take the cube root. So what is the smallest number I can take the cube root of that is a so let's see, perfect cubes are 1, 2 to the third is 8. There we go. So 8 is a perfect cube. So I can multiply the bottom by the cube root of 2, which means I have to multiply top by the cube root of 2. So the reason why I'm doing that is because I'm trying to get the cube root of 8 in my denominator. So if I do that, I'll get that. So this becomes, now the numerator is going to become the cube root of 10. And then my denominator is going to become the cube root of 8. Now, in this case right here, I can't take the cube root of 10, but I can take the cube root of 8. So I get the cube root of 10 over 2. So this is the process of rationalizing the denominator, which basically just means you're trying to take an expression that has a radical in the denominator and write it so that there is no radical in the denominator. Why that's such a thing, I really could not tell you. Even if there is such a thing, a reason, I just think that's kind of weird, but there you go. Alright, so write the expression in simplest form. So again, we have a radical in the denominator, so I'm going to multiply this by the conjugate, 9 plus the square root of 6 times by 9 plus the square root of 6. What I multiply to the denominator, I also have to multiply to the numerator. So in the numerator, I'm going to distribute. So this becomes 99 minus 11 square root of 6 over. Now, whenever I do the denominator, 9 times 9 is going to be 81. Whenever I multiply the outer and inner terms, they're going to cancel whenever you combine them. So I don't really care to do that part. And then when I multiply these together, negative square root of 6 times positive square root of 6, that becomes minus 6. So then the numerator, I still have 99 minus 11 square root of 6, all over 75. And now there's no radical in the denominator. So this is just using a method called multiplying by the conjugate. And I'll do the same thing here. I'm going to multiply by the square root of 8 plus or minus the square root of 7. But since I'm multiplying the bottom, I have to multiply the same thing by the top. And then I'm going to distribute that 2. So it becomes 2 root 8 minus 2 root 7 all over. When I multiply square root of 8 by square root of 8, that becomes 8. It doesn't really matter what the outer and inner terms are going to be, because when I add them, they'll cancel. And then that's going to become minus 7. So that's going to become 2 root 8 minus 2 root 7. And the square root of 8 is, so square root of 8 is equal to 2 root 2. So this becomes 2 times by 2 root 2 minus 2 root 7, which becomes 4 root 2 minus 2 root 7. Okay. So simplify this expression right here. So whenever I see these expressions, we're subtracting them, but they have the same roots. So now I can actually combine the coefficients of these radicals. So 8 minus 12 is going to become negative 4 and 6th root of 5. Here I can see that I'm subtracting these terms. They have they're being multiplied by 8 to the 3/4 power, which means I can actually combine their coefficients. So this becomes 9 times by 8 to the 3/4 power. Okay. Same thing here, except you notice here that I have these actually cannot combine when I want to add them, because this is the square root of 150, this is the square root of 6. So my guess is that I'm trying to simplify this one to have a root 6. So let me check and see if 150 is divisible by 6, and it is. So 27 root 6 plus 7, and then this becomes the square root of 25 times by 6. So 25 times 6 multiplies to be 150, and I can take the square root of 25. So this is 27 root 6 plus 7 times by 5 times by root 6, and so 27 root 6 plus 35 root 6, and now I can add these. So I can add 27 and 35. So then I get 62 root 6. Probably do the same thing here. So I can't add these together, these roots together, because they don't have the same radicand. So, but this one's cube root 2. I'm going to see if I divide 128 by 2. So 7 root 2 minus cube root, so cube root 128 divided by 2 is going to be 64. So let's do 64 times by 2, and the cube root of 64 is 4, so I have 7 cube root 2 minus 4 cube root 2, and I can add 7 and negative 4, so that's going to become 3 cube root 2. Same process here. Remember that 1/4 power is the same thing as 4th root. So 4th root 5 plus 6, 4th root of 405. And I'm trying to combine them, so I want the radicands to be the same. So 405 is divisible by 5. It's 81. So I have the 4th root of 5 plus 6, 4th root of 81 times by 5. And the 4th root of 81 is 3. So I have 4th root of 5 plus 6 times by 3, 4th root of 5. 6 times 3, I can do that part right there. So I have 4th root of 5. And then 6 times 3 is going to be 18. So 18, 4th root of 5. this is 1 fourth root of 5, so in all, I'm going to have 19 fourth root of 5. Alright, simplify these expressions. So we have cube roots. So I'm going to go by constants and then go by variables to see what I can take the cube root of. So I can't take the cube, wait, can I? 4 times 4 is 64. So the fourth root, or the cube root of 64 is 4. So I'm going to have 4. Okay. So then that's gone. That's not going to be in the third root anymore. The third root of r to the third power is going to be just r. So I can write r. So then that's gone. That's not going to be in the radical anymore. And then the third root of, so how about I explain it this way? So I know that the third root of 64 is 4. Now, I'm trying to see how many times 3 will go into these exponents right here. So how many times does 3 go into 3? Once. And so I can say r, and then there won't be any r's left over. So those are gone. Okay, and then how many times does 3 go into 6? It goes in twice. So then I'm going to have t to the power of 2, and nothing's going to be left inside the radical. And so there's no radical anymore. This is what I get when I simplify it. Okay, so then over here, the fourth root of k, so I'm doing the same thing. So how many times does 4, so I'm looking at the powers and I'm looking at the root. So how many times does 4 go into 16? 4 times. So I'm going to have k to the fourth. And then how many times does 4, or first of all, I actually have to do the fourth root of 16. So the fourth root of 16 is 2. And then the fourth root of z to the fourth, I see how many times 4 goes into 4, which would be 1, so it'd be z. And there's not going to be anything left over in the radical, so that's what I get. Okay, so for these ones right here, the third root of 125, I think that's just 5. 5 times 5 times 5 is 125, so I get 5. Okay, now I'm going to go through the same process. I'm trying to do the third root of r to the fourth, which means I'm trying to see how many times 3 goes into 4, which it will go once, but now I'm going to have 1 r left over. So again, so 3 goes into 4 at least once, which is why I'm going to have r to the first power out here, but there's still 1 r left over, so that's why there's still going to be 1 r in here. Okay, and then and then the third root of s to the 9 power, I'm going to see how many times 3 goes into 9, so that's going to be 3 times, so I'm going to have s to the third power, and now it goes in perfectly, so there's not going to be any s inside here, no s. And then for the cube root of t to the 7th, 3 goes into 7 2 times, so I'm going to have t squared, but then I'm going to have 1t left over. And so this is the expression right here. Going over here, so the fourth root of 405. Let's see, 405, does it have a fourth root? It does not. Okay, so I'm going to list fourth roots. So fourth roots are 1, 2 times 2 times, so 16. 3 times 3 times 3 times 3 is 81. And then 4 to the fourth is 256. I think that's about as far as we want to go. So 405, is it divisible by 256? It is not. Okay, then 405, we'll divide that by 81, and that's 5. Okay, so then the fourth root of 405 is equal to the fourth root of 81 times 5, and the fourth root of 81 is 3, so that's 3 fourth root of 5. So whenever I simplify this expression, I can bring out a 3, so I'm going to have 3 on the outside of my radical, but in my fourth root, I still have a 5 left over on the numerator. Okay, and then go through the numerator here. Hold up. So we'll keep this in mind, but let me, oh man. Let me back up just a bit here. That's good and all, but let's see if we can I just noticed that we can kind of simplify what's going on here. So I can go ahead and divide 405 by 5. So 405 divided by 5 is 81. Perfect. So this will become the fourth root. We're going to have 81. Now, x to the third over, so x to the third over x to the negative 1 is the same thing as x to the fourth, because I can write it as x to the third minus negative 1, because I can subtract their exponents because their bases are the same. So that's going to become x to the fourth. So x to the fourth, and then I have y to the third over y. This is to the power 1, so I can subtract their exponents. So this is going to become y squared. So I've made it so it's a lot easier to simplify the roots here. As we already established, the fourth root of 81 is 5, so I can bring a 5 out. And then the fourth root of x to the fourth, 4 goes into 4 once. So then I'm going to have x, and then I'm going to have the fourth root of y squared. And I can simplify this one right here. I know because I know 4 doesn't go into 2, but I can do this right here where I can write it as y squared raised to the 1/4 power, and then I can multiply those, so then I get 5x y to the 1/2 power, or you can say 5x square root of y. So both of those are fine. Okay. Let's see, perform the indicated operation. So I have a cube root of y and a cube root of y. So that means these are like radicals, and I can add those together. So that's going to become 21 cube root of y. As for 24, this one should be fun. So I can't add these together. They are not like terms. This is a fourth root of w to the 6. Let's see if I can get a w to the 6 over here. So fourth root of 16 is 2, so I can take out 2. And then the fourth root of w to the 10th, 4 goes into 10 twice, so that would be w squared. And then I would have left over w squared, right? So then I can write that as 2w squared, and I can write that as just square root of w, because I can simplify this the same way I simplified it up here. Add, y squared fourth root, w squared fourth root, so same thing. And then here for the next one, so that would be plus 2w. 4 goes into 6 once, so I can take out another w, which would make this w squared. And then I'd have the fourth root of w squared. So then I'd get the same thing, so plus 2w squared square root of w. Now I have the square root of w, and I have 2w squared square root of w, 2w squared square root of w, so that's going to become equal to 4w squared square root of w. Yeah, there's so much you can do with these, because then I can even just say that that's 4w squared w to the 1/2. And because these have the same bases, I can add these right here. So it's equal to 4w squared plus 1/2, which would be equal to 4w to the 5/2 power. So there's a lot you can actually do. But okay, and that should be everything for this homework assignment.